The derivative of a function is itself a function, which means that we could take the derivative again. In single variable calculus, there's only one type of derivative, so it makes sense for us to say the second derivative. But as we saw in the previous section, if you have a function of two variables, then you have two first-order partial derivatives. If we were to take another derivative, we would again have two choices. This means that there are four second-order partial derivatives. When looking at the notation for higher-order partial derivatives, it's important to understand the meaning of the symbols. You will notice that the two notations have the orders of the letters swapped for the same thing in the cross derivatives. The key to keeping this straight is to think about how parentheses would imply the order of operations. If you put parentheses around the subscript notation, you'll find there's only one reasonable way to do it. With Leibniz notation, the numerator takes some getting used to, but you can look at the denominator and think about parentheses to understand the order. The nice part about all of this is that if you know how to take first derivatives, you know how to take second derivatives. Just make sure to keep track of which variables are constant at each step. An even nicer fact is that for the functions that we will be working with, the mixed derivatives will always be the same no matter what order you calculate them. This result is known as Clairaut's theorem. The key technicality is that you need the mixed partial derivatives to be continuous near the point where you're taking the derivative. For all the functions we're working with in this class, that will always be true. However, there are examples where this condition is not met, and it's important to keep that in the back of your mind when working with mixed partial derivatives. Recall that in single variable calculus, the second derivative gave concavity. If the second derivative is positive, the curve is concave up. If the second derivative is negative, it's concave down. And if the second derivative is 0, then we don't know what the shape is going to look like. The second order partial derivatives xx and yy follow the same concept. This makes sense because both partial derivatives keep the same variable fixed, and so you're constrained to movement on a single plane. But the mixed partial derivatives are a bit more complicated. It turns out that the mixed partial derivatives give a measure of the twistiness of the graph. That's not a technical term, but it does convey the appropriate intuition. Let's take a closer look at it. Let's think about what f sub x sub y means. The inner derivative is the partial derivative with respect to x. In other words, it's the slope of f in the x direction. We are looking at the partial y derivative of this value, which is telling us how the slope is changing when we change the value of y. This can be difficult to visualize. We're going to imagine a sequence of traces in the x direction. We've sketched some planes in 3 dimensions to help you visualize what this looks like, and we're going to line up those traces on top of each other. We're going to fix a specific value of x, say x equals a, and draw the slopes of each of the traces at that point. If we align these slopes with each other, we can start to get a visualization of the slope changing as y increases. If you imagine the slope being like a surface that you're riding on, you can see that it's twisting a bit to the right as time moves forward. That's the idea we meant by twistiness earlier. In this case, the slope is decreasing as we move forward, so f sub xy is less than 0. And the larger the value is, the faster we're twisting. This is a quick visualization of the second derivative. We'll leave it as an interesting mental exercise to think about what's happening in the other direction with f sub yx, and in particular why these two values are the same if things are nice and continuous. These pictures tend to be easier for people who are more visual than those who are less visual, and that's okay. It's the practice of learning to think carefully about the meaning of these pictures that matters, not that you can do it quickly or that it's intuitive. As you continue along in mathematics, you will want to focus on the practice of thinking carefully much more than you will want to focus on thinking quickly. This is counterintuitive for a lot of students, as they tend to think that better and faster mean the same thing. That's just not how it is. You want to move towards the idea that clearer and more precise thinking is better, because that's the skill that will sustain you when things get more difficult.